So when working with vectors and mechanics, you can more or less use Suvat in the usual way, and I'm going to quickly show you how to convert the Suvat equations to vector notation. So one you might be familiar with is V equals U plus AT. Now, obviously a very useful equation, but only works in one dimension. How can we make it work in two dimensions? Well, V1, V2 equals U1, U2 plus AT. Now, you might notice here, I'm not going to write T as a vector. T is always going to be a scalar because T doesn't have any sort of direction or anything. We're just talking about how much time has passed. T stays as a scalar here. So, next equation we'd have S equals UT plus a half AT squared. And again, we can change this to vector form. So we could have S1, S2 equals U1, U2 times T plus a half AT squared. So we're going to have A1, A2, T squared. Okay. So what next? We can have S equals a half U plus V times T. So how will this change? Well, I'm sure you can work it out by now. We'll have S1, S2 equals a half U plus V. So we're going to have double brackets here. We're going to have U1, U2 plus V1, V2, close both the brackets, times T. Okay. And then we'll have S equals VT minus a half AT squared. Well, how can that change? We'll have S1, S2 equals V1, V2 times T minus a half A1, A2, T squared. Okay, so that's all of them. And you might be thinking, well, that's only 4. In Suvat, we use 5 different equations. So the one I've missed off is V squared equals U squared plus 2AS. And the reason I missed it off is because of this last little bit here. Because it's AS, you would have a vector times a vector, which might not give us the solution that we expect. So we're not going to use it here. We can just ignore that equation. So when working with vectors, we'll only use those 4 there. Okay, this can also be expanded. So at the moment, we're only using 2 dimensions. So you could sort of imagine the top one as the X direction, the bottom one as the Y direction. If you like, this can be expanded to as many variables as you want. So for example, expanding it to 3, if we expand the top equation to 3, we could have V1, V2, V3 equals U1, U2, U3 plus A1, A2, A3 times T. So you can see I can expand it to as many variables as I want. I can expand it up to whatever I like. It could be 10 variables, it could be 20 variables, as big as I want, n dimensions. A-level mechanics, we only tend to work with 2 dimensions, but they can ask with more. You just apply it in the exact same way. So using non-uniform acceleration with vectors, we use it in the exact same way that we would when we discussed Suvat previously. So for example, we could have V1, V2, and what equation can we use to relate it to one other variable? Well, 2 others, I suppose. Well, we could do the derivative of S1, S2 over dt. So the derivative of a displacement vector with respect to time is a velocity vector. Similarly, we could do A1, A2 equals, it's the derivative of a velocity vector with respect to time. And of course, you can go in the opposite direction as well. So you could have S1, S2 is the integral of V1, V2 with respect to time. And we could have V1, V2 is the integral of A1, A2 with respect to time. Okay, and again, I've only mentioned 2 dimensions, but you could do it up to n dimensions. And you could also use I and J notation as much as you want. Okay, so it's just simple differentiation or integration, and you would just integrate the top component separate to the bottom component. So, for example, if we had A1, A2 here was, let's say, 2t, and then let's say 5t, well, integrate them separately. What would we get? We would get t squared, and we would get 5 over 2 t squared, and then plus some c. So you can just differentiate or integrate to go between them.